guys, here is your next set of notes for Unit 6. Today we're talking about solid states. So solids can be separated into two categories. There's crystalline solids, which are made of repetitive units and sometimes repetitive features, and those are visible on the macroscopic level, which means we can see them easily. And examples of those would be salt crystals, snow, gemstones. They all have kind of a crystal structure to them. There's also amorphous solids that don't have well-defined 3D structures. Examples of these are going to be lots of plastics and glass. The strength of any solid depends on the molecular forces that hold it together. So you can have physical bonds, which is going to be like intermolecular forces. You can also have chemical or intramolecular forces. So obviously chemical or intermolecular is going to be a lot stronger than physical. Remember that intermolecular forces is going to be like the bonds that hold different molecules together. So if I have like a water molecule and another water molecule, the bond that holds those two together would be intermolecular. Intramolecular is inside the actual molecule. So if I have a H2O molecule, the bond between the O and the H, that's intramolecular. Those are harder to break. Remember that elements and compounds can crystallize. So there's 4 different types of crystalline solids. There's network covalent, which is that diamond. There's ionic, which is that kind of silver rock looking thing. There's metallic, which is the gold picture. And then there's covalent or molecular, which would be the snowflake. Here's a few more examples that show all of those different types of solids and what they look like on a molecular level. The strongest of these being the network covalent. So let's talk about each one. Molecular solids are going to be your weakest. They consist of atoms or molecules that are held together by intermolecular forces, so weak physical bonds. Those are going to be easy to break. Examples would be neon, solid neon. So neon's a noble gas. Noble gases really don't exist as solids. It's super rare, so that's something that would easily break apart. Solid water and CO2 are other examples. Next, we have metallic solids, which consist of a positive core of atoms held together by a sea of electrons. That's going to be your metallic bonds, which are generally your transition metals on the periodic table. All of those have a sea of electrons. Examples would be iron, silver, and copper. So it's stronger than the molecular solids, but still weaker than our other two. Next, we have ionic solids. They consist of cations and anions held together by the electrical attraction of opposite charges. Those are going to be held together by intermolecular forces. So it's when you have like a metal and a non-metal, their electrons are being transferred. There's electrical charges because one of them's positive, one of them's negative. Those are going to be a lot harder to break. Examples of this would be cesium chloride and sodium chloride, really any ionic bond. Next, we have covalent network solids. These are your strongest solids. They consist of atoms held together in large networks or chains, by intermolecular chemical covalent bonds. Examples would be diamonds, graphite, asbestos, and quartz. So properties of molecular solids, again, these are really weak bonds, like a hydrogen bond that's shown in the picture as a dotted line. Those are easy to break. They have low melting points because they break apart so easily. They're brittle and they're non-conducting. Next, I have properties of metallic solids. These are going to have a little bit higher melting points because they're really just made up of metals. And then they're extremely hard, they're malleable, they're not brittle, they conduct electricity. Why? So again, these electrons are moving in a sea of electrons, they're moving freely between all the metal ions. Generally, since they're just metals, that's one of the reasons why they're malleable, they're not brittle, and they conduct electricity. Those are just properties of metals. Here's another picture just to show you what those electrons are doing. The outer electrons are weakly bound to the metal atoms that they're free to roam across the entire metal. Having lost their outer electrons, individual metal atoms are more like positive ions with just lots of electrons floating around. Next, we have ionic solids. These have high melting points. They're brittle, they're hard, they're non-conducting as a solid, but they are conducting as a liquid. Again, there's a picture of what that looks like off to the side. I have sodium chloride shown there. These are a little bit stronger than the other two mentioned, but still weaker than the next one. Next, I have covalent network. These have really high melting points. They're really hard. They're not really conducting. The bonds between each atom are very difficult to break. Here's another example of that. So diamond and graphite, both of those are just chains of carbon. The difference is on graphite, there's weak bonds in between those layers. With carbon, it's more of a crystal shape. Another man-made network covalent solid is something called nanotubes. So on the left, the thing that kind of looks like a rainbow, that's a ball and stick model of a nanotube with carbon atoms and a 6-membered ring bonded in a honeycomb shape. Nanotubes have strands narrower than human hair, but 10 times stronger than steel. So these are used a lot in the medical field. It's just a cool thing that uses chemistry. Next, we're talking about a crystal lattice. It is the ordered structure that we generally just refer to as a crystal. One unit of that crystal is called a unit cell. The unit cell is the repeating pattern that's just repeated throughout the entire crystal or the entire object. The crystal lattice is a collection of all the unit cells. So the crystal is what we actually see, even though it's made up of tiny little cells. The frame of reference for each unit cell must be the same, whether it's the center of an atom or the corner or whatever. So here's a picture of that. The tiny little points are called lattice point. That's generally one of your atoms. A unit cell would be one of the squares or one of the cubes. And then the entire lattice or crystal shape would be all of those cells put together. Here are some of the different types of unit cells. Really, the main one that you need to know is cubic. There's pictures to kind of give you an idea of what those look like as well. So here are 3 possible cubic unit cells. There's simple, there's bodied, and there's face-centered cubic cells. Simple means that the lattice points are at the corners. Body means there's one lattice point in the center, but there's also lattice points on the corners. And then face-centered is there's a point at each corner and each face and in the middle. So as you go down on this chart, there's the cells get a little bit bigger because there's more parts of the atom showing up. So also as you go from top to bottom, the packing efficiency gets higher, which means that they're able to just pack more atoms in one cubic cell. Some solids crystallize in a layering system, which is called packing structures. In a molecular solid or metallic solid, the unit cells are packed so that the interactions are maximized. This is achieved by minimizing the distances between atoms which exhibit attractive forces. So the whole point of a unit cell is to get the atoms as close together as possible. Kind of like if you had a box and you filled it with ping pong balls, the ping pong balls would move a little bit so that they would pack down as much as possible. Here's a couple more examples of just showing what packing is. It's just showing you that they're going to become as close together as possible. You really don't need to know specifics on this, just kind of know that it's a thing. There's also something called X-ray diffraction. So crystals and atoms, the dimensions can be experimentally determined using X-ray diffraction. Sir W.H. Bragg and his son developed this technology or this technique in 1913. X-rays scattered from 2 different atoms may reinforce or cancel one another. So here is a little bit of what that looks like. Okay, so in X-ray diffraction, I have an X-ray tube shot through a lead screen straight at a crystal. And then it's going to produce a lot of spots on this photographic plate. And that's going to kind of give us an idea of what crystal it is and how it's packed and so forth. You can do a lot of math to calculate some of these things that's shown in that picture at the bottom with the little waves on it. You can calculate X, Y, Z, and D, all kinds of stuff. However, you're not going to need to do that this year. So really just know that X-ray diffraction is something that you can use on crystals. Okay, that's it. Make sure you do your practice problems and let me know.